The first one is inductive effect. What is inductive effect? Inductive effect is the polarization of one sigma bond by adjacent sigma bond. Polarization of one sigma bond by adjacent sigma bond. So this can be explained by taking an example of chloroethane. CH3, CH2, Cl. So here we are finding only the sigma bond. This chlorine, it has most electronegative than the carbon. So the chlorine, it has a tendency to withdraw its shared pair of electron towards the chlorine atom, and that movement of electron towards the chlorine to be represented by an arrowhead over the covalent bond. So this is what the movement of electron towards the most electronegative atom. So due to the shifting of sigma bond from carbon to chlorine, it develops a partial negative charge over the most electronegative atom and a partial positive charge over the less electronegative carbon atom. So this molecule, as it has two carbon atom, let us designate this is C1 and this is as C2. So this pulling of electron, as it develops a partial positive charge over the carbon, that can even be influenced by the adjacent sigma bond. So the carbon C1 that pulls the electron sigma bond towards itself, and hence it develops one more partial positive charge over the second carbon atom. So such a way, how many carbon are there in its length? All the electrons will be moving towards the most electronegative atom, and the movement of electron towards the most electronegative atom is given by an arrowhead over the covalent bond. So this is what known as inductive effect. Suppose if I write a molecule having 4 carbon atoms, CH3, CH2, CH2, Cl. In this you may find the length of the carbon chain increases. So this is also, it develops del minus, it is del plus, it is del del plus, it will be 3 del plus, and here it goes 4 del plus. So the quantity or the amount of the partial positive charge over the first carbon is somewhat high, but when you go from first carbon to fourth carbon, the amount of positive charge associated with the carbon atom goes on decreasing when the carbon gets away from the electronegative atom. So we can say that the amount of partial charge or the quantity of partial positive charge associated with the carbon atom goes on decreasing when the length of the chain increases. And this inductive effect, which can be influenced by the nature of the substituent present in a molecule. What are called nature of the substituent? We have two types of groups. One is called electron donating group, and the other one is electron withdrawing group. So the electron donating group used to donate the electron towards the another molecule. So in this example, we find the chlorine atom that receives the electron to who is donating only the alkyl group. So we can say the alkyl groups are electron donating group. What are alkyl group? CH3 group, CH3 CH2 group, or we can say isopropyl group, or we can say tertiary alkyl group, CH3 thrice C. So these are all known as plus I groups, which are called plus I groups. So plus I groups usually releases the electron, or those are electron donating groups. Similarly, what about electron withdrawing group? Electron withdrawing group, they used to pull the electron from the carbon atom. Such groups are OH, alcohol, or we can say NO2, or alkoxy group, or carboxylic acid group, or aldehyde group, and even amino group. See, these are all having a tendency to pull the electron towards themselves. So these are called electron withdrawing group, and these electron withdrawing groups are represented as minus I. So the effect which is caused due to the electron donating groups is known as plus inductive effect, and the effect which is influenced by electron withdrawing groups is known as minus I effect. So, inductive effect we can say by plus I effect and minus I effect. Plus I effect is due to electron donating group and minus I effect is due to electron withdrawing group. Okay, how to classify them as they are electron donating and electron withdrawing? This is with a reference to hydrogen only we are classifying. So, if at all the hydrogen is neither a plus I group nor minus I group. So, the plus I value of hydrogen with respect to that, the one which can able to donate more readily than accept is classified as plus I groups, and the other which can readily accept the electron then releasing is referred as minus I groups. Okay, this is what inductive effect. The second electron displacement effect is resonance. What is resonance? Before understand about resonance, we need to know some of the molecules whose properties or their behaviors cannot be explained by any of its single structure. For example, let us take carbon dioxide. Carbon dioxide, it has the structure of C double bond O double bond O, and in which the oxygen it has two lone pairs of electrons over it. See, this molecule it has pi bond as well as the oxygen it has an octet structure. The oxygen atom it has an octet structure, that means it has 8 electrons in its structure. And this oxygen we know well more electronegative than carbon, and this carbon this side is also attached with another oxygen atom of more electronegative. So, in this structure, this oxygen when it withdraws the electron from the carbon, one of the pi bond from the carbon oxygen double bond, subsequently this oxygen it releases its lone pair electron towards the carbon. This is why when the pi bond is getting over the oxygen atom, the electron density of carbon decreases. So, to satisfy the electron density of carbon, the oxygen it gives away its lone pair electron towards the carbon atom, and hence this makes oxygen triple bond, carbon, oxygen single bond, but it has 8 electrons, 3 pairs of electron with the negative charge, and this oxygen has given its lone pair electron and gets it is a positive charge. This is one of its form. The other way we can represent the reverse of the structure. See that now you can say this oxygen it withdraws the electron towards itself. So, we can represent in this way. This withdraws the electron. So, the oxygen it gets a negative charge. This carbon whose electron density lowers, and hence this oxygen it gives away its lone pair electron to the carbon. So, this structure we can represent like this. See, here it is a triple bond, oxygen, that pair of electron given away, so it is getting a positive charge, and the double bond is into a single bond. Now, already oxygen has 2 lone pair, it has received 1 more pairs of electron, so it gets 3 pairs of electron with the negative charge. Here it is a positive charge. So, you may find the charge separation among the bonded atoms. The one thing we said about the movement of pi electron from one to the other, that is called delocalization of pi electron. But the sigma bond, among the 2 bonds, one of them is sigma, the other one is pi. Sigma bond never be delocalized, it is a fixed one. It is actually bonded between the 2 atoms. But the pi bonds, it has a tendency to move over more than 1 atom. So, the movement of pi electron among more than 2 atoms is said to be delocalization of pi electron. See that this molecule you are representing with 1, this is 2 and this is as 3. So, if I want to explain about the properties of carbon dioxide, either of the single molecule, that is structure, cannot explain its entire property. So the property of such molecules can be explained by the three different contributing structures of carbon dioxide. So this is what we are saying resonance. So a molecule, such a way we can have several molecules. Wherever you are finding the multiple bond with an octet structure of an element in its molecule, you can represent that resonance. Similarly, let us take an organic compound benzene. Benzene is a 6-membered ring. It has 3 pi bonds in its alternate position. So let me represent 1, 2, 3, 4, 5, 6. You may find the pi bonds are present between 1, 2 position, 3, 4 position and 5, 6 position. Now I can give its electron delocalization of pi electron this way. So I can write its another canonical structure as 1, 2, 3. So the numbering we can say now 1, 2, 3, 4, 5, 6. See that? In the previous structure, you are finding the pi bond between the carbon atoms of 1 and 2. But in this structure, you are finding the double bond or the pi bond between 2, 3 position. This is what delocalization of pi electrons within the ring of benzene. So this gives rise to the two structures 1 and 2. Let us discuss about the property of benzene molecule. This benzene, it has carbon-carbon single bond as well as carbon-carbon double bond. The carbon-carbon single bond in hydrocarbon actually whose bond length is 154 picometer. And in an alkane, the carbon-carbon double bond is 134 picometer. So what we have to imagine, the carbon-carbon sigma bond, it must be 154 and the carbon-carbon double bond should be 134. But actually this is not taking place. The bond length of all the carbon-carbon that becomes only 139 picometer. So the carbon-carbon bond length is equal to 139 picometer. This is not only for any of the 2 carbon, it is equal for all the 6 carbon atoms. So all the 6 carbon atoms, they have the bond length of 139 picometer. So now you can conclude the resonance is due to the delocalization of pi electron, which gives rise to more than one structures. And the properties or the behavior of the molecule cannot be explained through either of the structure. It can be explained only by its all the contributing structures. This is what actually resonance. So such a way, what are the conditions for the resonance? See, in this resonance, you may not find the movement of the nuclei. What do you mean by nuclei? The atoms which are representing the molecules, they are in their own position. They do not move. But you are finding only the movement of pi bond. Only the pi bond you have to consider here. So the delocalization of pi bond takes place. At the same time, the number of pi bond remains same. In this case, you are finding there are 2 sigma bond and 2 pi bond in carbon dioxide molecule. In all the molecules you may find this is 1 sigma bond, this is 1 sigma bond, the other 2 are pi bond. So this also has 2 sigma bond and there are 2 pi bond. In this case, one of them is sigma bond, the other 2s are pi bond. This is a sigma bond. So you are getting 2 sigma, 2 pi bond. So what we can say? During the delocalization of pi electrons, the number of pi bond or the total number of pi electrons will never change. This is what the condition for resonance. Nuclei do not move and the pi bond, number of pi bonds remains same. Okay. What about the stability of the molecules considered? See, the stability of the molecule depends on the number of covalent bonds. How many bonds are there, that many structures we can arrive. And the number of resonating structures. I represented only 2 structures for benzene. But carbon dioxide, it is the contributing structures of 3 structures. So number of resonating structures increases, stability of the molecule also increases. And the third point, the charge separation. You may find it has the carbon dioxide molecule, one oxygen carries a negative charge, the other carries the positive charge. This is called charge separation. The charge separation must be smaller. And each oxygen atom or even the carbon atom, or in this case the hydrogen atom, should have its octet structure. But hydrogen is an exceptional case, it has duplet structure. So these are what the conditions to be satisfied for resonance, and it explains about its stability of the molecules also. So let us see what is resonance effect. Resonance effect is also known as mesomeric effect. Resonance effect is given by the letter R, or the mesomeric effect is given by M. What is resonance effect? Resonance effect is due to the interaction of two pi bonds or one pi bond with lone pair electrons, that is known as resonance effect. Okay, so in this resonance effect we are going to discuss about what is plus R or plus M effect. Plus R plus M, plus resonance or plus mesomeric effect. Just like inductive effect. Inductive effect we classified as plus I and minus I, depends on the nature of the substituent. Similarly, depends on the nature of the substituent in a compound, we can have plus R effect or the minus R effect. Let us take first of all plus R effect, that can be explained by taking an example of phenol. Similarly, let us take minus R effect also, or minus M effect. For this, I am going to take an example of nitrobenzene. This is phenol, this is nitrobenzene. So let us discuss first of all phenol. Phenol, that oxygen atom, it carries two lone pairs of electron, 1, 2, and it is bonded with the sp2 hybridized carbon atom. The oxygen is bonded with sp2 hybridized carbon atom of benzene ring, and we have to find the interaction of a pi bond or a pi bond with the lone pair electron. See, oxygen atom has a lone pair electron, ring has pi bond. Okay, so there is an interaction between the lone pair and the pi bond. How it will take place? It is depending upon, once again, the difference in electronegativity of the substituent and the molecule. This sp2 carbon is more electronegative than the oxygen atom. So what it will do? It will withdraw the pair of electron towards the ring. So the carbon atom valency is actually 4 only. When it withdraws the electron, the valency of carbon it goes 5. So to satisfy the first carbon's valency, this electron it just comes out. So you can find once again carbon gets the 4 electron. So I can write its resonating structure. Benzene ring. Now the single bond is into a double bond, to which oxygen donates the electron, so it gets a positive charge. And the electron between the 1-2 position comes away, so I am getting the negative charge at its place. And the remaining electrons are over here. I told there is a delocalization of pi electron. So this pi electron, it gets delocalized such a way. So I can have the second resonating structure, a benzene ring with the double bond of OH group. The electron which is at the second position enters into the molecule. So I have, this is a pi bond. And the electron present between these two carbon atom comes out, and I am representing the negative charge is at the 4th position of the carbon. Now it has another double bond over here. Next thing, once again the delocalization occur. So what happened? This pi electron, the negative charge, it enters into that, and this pi electron goes to the 6th position of the carbon atom. So for this, the resonating structure will be the position, already it has one pi electron, this negative charge enters there. So here you are getting one more pi electron, this pi electron goes to out of the one, so the 6th position it gets the pi electron, that becomes the negative charge, sorry. So here you have oxygen with plus, okay. This is what? The delocalization of pi electron. What would be the last one? Yes, correct. This negative charge enters into the ring, oxygen withdraws its electron. So we are making the last molecule of the resonating structure as such that of the first one. So OH with the lone pair, 1, 2, 3, that's all. See, the position of double bond is different from the first molecule to the last molecule. So if I represent the numbering of carbon atom, you can find how the position of pi bond gets altered. This is 1, this is 2, this is 3, 4, 5, 6. Here this is 1, this is 1, 2, 3, 4, 5, 6. Find the position. In the first resonating structure, you are finding the double bond between 1, 2, 3, 4, 5, 6. Here it is among 1, 2, 3, 4, 5 and 1, 6. This is what? Resonating structure. This we should know, we have to learn. Okay, one more thing. I have to represent the resonating structure among the one. The doubly arrow head that represents the resonance effect of the molecule. The resonating structure should be connected with a doubly arrow head. And moreover, how the molecule it gets changed from one to another. Whether it will take place on its own? No. It requires a small amount of energy to change from one contributing structure to another contributing structure. What is called that energy? It is known as resonance energy. That is known as resonance energy. The resonance energy should be minimum. Minimum means at room temperature itself the resonating structure should be allowed. That is what the energy required for the resonance will be minimum. So how the resonance energy is calculated? It is nothing but the difference in energy of the actual molecule and among the contributing structure, the one which has the lowest energy, that gives rise to resonance energy. So you can write resonance energy is the energy of actual molecule minus the lowest energy of contributing structure. That is called resonating . That is called resonance energy. Okay. Now let us discuss about minus R or minus M effect. Same way, same thing. In the previous case, you found the negative charges at their second position, fourth position and the sixth position. But in the following structure, you will find a total difference among the charge of molecule. So let us come to the minus R or minus M effect. In this case, we have taken on example of nitrobenzene. Just find the difference of the substituent among these two molecules. The first molecule has OH group, the second molecule has nitro group. What is the difference? Yes, it is there. In the first case, oxygen is bonded with hydrogen, which is less electronegative. But in the second case, nitrogen is bonded with oxygen, which is more electronegative. So the atom that finds which the difference of electronegativity among the bonded atom. In the previous case, the difference of oxygen and hydrogen electronegativity and that of oxygen carbon electronegativity, where it finds maximum, to that direction the electron it finds to move. In this case, oxygen is more electronegative than the nitrogen. So oxygen withdraws the electron and hence nitrogen has to withdraw the pi electron from the ring. So the movement of electron just gets reversed as that of the previous one. The previous one, the electrons going towards the ring. In the second case, the electrons are just moving out of the ring. Let us discuss how. Oxygen withdraws the electron and hence simultaneously nitrogen withdraws the electron. In this, between the nitrogen and oxygen, there would be a positive and negative charge because of its sharing of its lone pair electron to the oxygen atom to satisfy its octet theory. Okay. Now this oxygen, as it gives away the electron to the nitrogen, you are finding a positive charge over the second carbon. And this positive charge is now attracted by the negative charge. So the movement of electron, it goes towards the positive. So we will write the second resonating structure for this molecule. So N double bond with the O minus. This is minus, here it is a plus, and this plus, this electron, it moves towards the ring. So let me take here the structure 1, 2, and the second position takes a positive charge. Now this positive charge will be attracted by the adjacent pi bond. So the movement of electron towards the positive charge. Now the positive charge is developed at the fourth position, this position. So we can write its hybrid structure, double bond, here a pi bond and double bond with the oxygen minus, with the oxygen minus, nitrogen carries a plus, and in this case the plus charge is at the fourth position of carbon atom. And one more resonating structure we can draw. This pi bond that pulled by the positive charge. Now the sixth position of the ring will get a positive charge. So here let's take double bond N with the O minus, with O minus, and the positive charge is at the sixth position. Now it has to approach its final. That's why this pi bond comes inside and this pi electron, that negative charge between the nitrogen oxygen moves. So we are getting the other molecule N double bond O, oxygen minus plus, a bond, bond, bond. That's all. So this is the resonating structures of nitrobenzene. So previous case, you may find the lone pair of electrons from the substituent is attracted by the ring. In the second case, the pi bond of the ring is attracted by the substituent. So when the substituent withdraws the electron from the ring, where the ring finds positive charges at the 2, 4, 6 position, whereas whether the ring is more electronegative than OH group or any other groups, what happen? The movement of electron takes place towards the ring, in which cases you may find the 2, 4, 6 positions having negative charges. So this is what caused by plus R effect and minus R effect. And the groups which are lead to, that is the developing negative charges at the 2, 4, 6 position are called minus plus R groups, are called plus R groups. The plus R groups example we can write OH, alcohol, alkoxy group, or we can say NH2 group, primary amine, secondary amine, all the amines that belongs to plus R group. The plus R group usually develops negative charges at 2, 4, 6 position, and the minus R groups are NO2, nitro group, aldehyde, ketone, carboxylic acid and acid halide. These are all minus R groups. That's all. Electromeric effect. what is called electromeric effect? Before that, this electromeric effect is a temporary effect. And this temporary effect, this can be influenced by an attacking reagent only. Suppose if I have a molecule with the multiple bond, either a triple bond or molecule with the double bond. See, to exhibit the electromeric effect, the molecule must have a multiple bond system, either a double bond or a triple bond. Suppose if at all the molecule is influenced by either an electrophile or by an nucleophile. The first case H plus I have given, so it is an electrophile. The second case Cn minus is given, the negatively charged one, so this is a nucleophile. So depends upon the nature of the attacking agent. The H plus and Cn minus are attacking agent, which will attack the multiply bonded reactive system. See that? This is H plus, it will go to always the negative charge. So depends on the nature of the attacking reagent, the multiple bond system will transfer its pi electron to the other atom. For example, if I write here, the oxygen carries the negative charge, this carbon donates its electron, so this carbon gets a positive charge. Now I can write the system with double bond here. This carries a negative charge to which the hydrogen will attack. So I am getting hydrogen, this is a bond. So this is what electromeric effect, and in which this effect is caused by an electrophile. So it is called plus E effect, that is positive electromeric effect. And in the second case, I have taken a nucleophile as an attacking agent. Nucleophile, where it will attack? The species with the positive charge. So in which, due to the demand of nucleophile, the carbon where it goes takes away the electron, to the opposite the Cn minus will attack. So my compound will be Cn with a single bond of this is, so this carbon it carries a positive charge. See the difference of these two species? The previous one, carbon carries the positive charge because the attacking reagent is an electrophile that seeks the carbon with more electronegative, the carbon carries with the negative charge, so you find the compound here. But in the second case, I have taken an attacking agent of nucleophile. This nucleophile that seeks only the carbon with the positive charge. So the pi electron that gets shift over to the adjacent carbon atom, that develops a positive charge to the previous carbon atom to which the cyanide is attacking. So we are getting the compound. Such effect is called minus E effect or negative electromeric effect. This is what electromeric effect. Last topic of electron displacement effect is hyperconjugation. Hyperconjugation is just to stabilize the molecules through the interaction of sigma bond, and it is also called no bond resonance, and this effect is also permanent effect. So in this, the sigma bond only being shared, that means it gets delocalized with the species having an unshared p orbital or with an sextet structure or with the positive charge. Let us see an example of ethyl carbocation CH3CH2 plus. This carbon, it has 3 hydrogen atom of the filled p orbital, that is sp3 orbital. So here it has the bond, each bond can have a 2 electron. So the carbon sp3 carbon, it overlaps with 1s orbital of 3 hydrogen atom, and it is with CH2. Here also the 1s orbital of hydrogen bonded with C, but the carbon carries the positive charge. So when it carries a positive charge, it has a p orbital, but that p orbital is an empty orbital. So this is a 2p orbital of carbon, an empty orbital. So this ethyl carbocation to be stabilized through the hyperconjugation. What will happen? sp3 carbon and the 1s orbital of hydrogen, it has a pair of electron, the shared pair of electron. The shared pair of electron, it can interact with the empty 2p orbital like this. It can interact with the empty 2p orbitals of this CH2 carbon. So what happens if I write in the structural way, CH3, CH2, here it has a positive charge. This hydrogen, the sp3 carbon and 1s hydrogen that makes a bond, it gets interact with carbon with the positive charge. So it takes C hydrogen, hydrogen, but this hydrogen has given away its electron. So hydrogen carries the positive charge. Here the single bond goes double bond and this becomes CH2 group. And this carbon, it has still 2 more hydrogen atom. So how many hydrogens are there? That many times the interaction can undergo. So we can write the another interaction. This hydrogen which can interact over here. So I can write this is now H plus carbon, hydrogen, hydrogen, double bond CH2. And one more CH bond I have. So I can write the next hyperconjugating structure. Hydrogen with the carbon and this hydrogen with the positive charge doubly bonded with CH2 group. This is what? The delocalization of sigma bond. Actually I said the sigma bond never undergoes delocalization. But here the molecule, it gets stabilized. See, the hydrogen would never be gone out of the structure. It is just intact with the structure. Only to stabilize that carbon with the positive charge, the hydrogens that can provide its filled orbital to the unshared 2p orbital of carbocation. This is just for stabilizing the molecule, nothing for any chemical reaction or else. That's what we discussed in our stability of carbocation. I told there are 4 terms that can able to discuss about the stability of carbocation. One is inductive effect and hyperconjugation, electronegativity, resonance. This is what the hyperconjugation, how it stabilizes the carbocation. So in this case I have only methyl group. So the methyl group, it has given by the 3 more hyperconjugating structure. If I have tertiary carbocation CH3, CH3, CH3 plus. So in this case every carbon, the sp3 carbon has 3 hydrogen atom and every CH bond that can interact with the 2p orbital of C plus. So how many structures are possible? About 9 structures are possible. Methyl 3 only, so it gives rise to 3 structure, and in this case such a way every methyl group it gets stabilizing through the conjugating structure. So you will get 9 number of conjugating structure. That's why tertiary carbocation is more stable than primary or even secondary. Okay, the next one, let us discuss about how the hyperconjugation is taking part in an alkene system, that is the doubly bonded system. Doubly bonded system, it will have a pi orbital. So we can have an example of. So let us find how the hyperconjugation is observed in doubly bonded system like propene CH3, CH double bond CH2. This I can write in their overlapping way. CH3 carbon, it has a behind, that means the out of the plane one hydrogen is there, so we can write CH3 here. And carbon carbon sigma bond 1 I have and carbon carbon pi bond I have. So I can link this carbon, it gets overlapped with hydrogen atom and the one more overlapping with the carbon, and that carbon has hydrogen of the terminal CH2. And both of the carbon, they have their 2p orbital which is having 1 electron each. So that I can represent such a way. So this is 2p1, this is 2p1. These 2p orbital that gets that makes the side wave overlapping. That side wave overlapping only it causes the pi bond. The axial overlapping gives a sigma bond. both of the carbon here, they are sp2 hybridized. The first carbon is the saturated, so it is sp3 hybridized. In the sp2 hybridized carbon atom, both of them will have the 2p orbital of its own having 1 electron each. So these two 2p orbital that overlaps sideway to form this pi bond. Okay. Now let us take the structure CH3. CH double bond CH2. Hyperconjugation, the bond should, the sigma bond has to move. Like how it can go, this pi electron is being attracted by the terminal carbon. Subsequently, this carbon, that is the carbon hydrogen, it interacts with the adjacent carbon. So we will have CH plus hydrogen, this single bond with the double bond, and in this case you have a hydrogen here CH2 group. The terminal carbon, as it withdraws its lone pair electron, so you can represent with the negative charge. Similarly, you can write two more hyperconjugating structure with the rest of the two hydrogen atom. So we will get H plus carbon, hydrogen, double bond, CH2 with negative charge. And one more, this hydrogen will take, so CH2, H plus, double bond, CH2 with lone pair electron, that is the negative charge. I think we are going to close this. Before that, just I give a snap about it. We have seen inductive, resonance, electromeric, hyperconjugation. Out of this, the inductive effect is due to the sigma bond, and the electromeric effect and resonance and all due to the pi bond. Hyperconjugation is due to the sigma bond, it is delocalization. And in the previous cases, they will undergo polarization. Here there is no polarization. Okay children, we completed today's session. The next class with the new topics, let us see once again. Until then, bye bye.